Hello everyone. I'm thrilled to present our research on Mycosis Fungoides detection using deep learning. Our team, under the supervision of Professor Mohamed, we developed a deep learning pipeline to modernize and accelerate the diagnostic workflow of the MF. So, every day, our skin acts as our primary shield, absorbing the impact of the environment, sunlight specifically. But as we zoom in past the surface down to the cellular level, the most dangerous threats are the ones that hide in the plain sight. As you can see here, cellular patterns can silently mutate, and there is a microscopic battleground where early detection is the only defense. So, mycosis fungoides, the disease we are targeting in our research, can hide very well. In the clinical world, it is known as the great imitator. It is a rare type of T-cell lymphoma that mimics eczema and psoriasis in its early stages. As you can see in the figure to the right, mycosis fungoides, when diagnosed at an early stage like 1A or 1B, it has a very decent chance of survival rate, but if it is misdiagnosed or caught at a late stage, it's the difference between life and death. If it progresses to like an advanced stage, as you can see, like 2B, it's very deadly. That's why at a late stage, people usually, when diagnosed with late stage mycosis fungoides, have only 3 to 5 years on average. As you can see, how can we catch it today? The burden falls entirely on the shoulders of pathologists. They are tasked to find a needle in a haystack, require immense effort and probably frustration, as you just saw, too many slides and very high magnification. It's not just one biopsy, it's several biopsies from several patients. So here where we step in, we partnered with the clinical dermatologist from Al-Ainy teaching hospital in Egypt, where we acquired about 40 gigabytes of histopathology images. This is a sample from the images I'm showing here, and we have those images from roughly 242 patients, and our task is to take those images and feed them into a deep learning pipeline where we can at the end output the prediction whether this patient is diagnosed with mycosis fungoides or not. As you can see, the dataset we received, it's consisting of two magnifications, 10 times and 20 times. I'll explain our methodology now. As you saw the data we just received, we take this data and we divide them into patches, each one a size of 512 by 512 and the stride of 256, creating a 50% overlap. Then after we divide the image into small patches, we filter them using the HSV color space to remove background noise and preserve only the diagnostically relevant tissue. After doing that, we have the patches, only the region of interest from each image. For example, those on the edges or containing the background are now discarded. Now we use the Optuna framework for finding the ideal parameters. In the future, we will use a deep learning framework like ResNet or FishNet, but we don't know what parameters to use, so we use the Optuna framework to optimize the parameters. We basically searched for the optimal learning rate, weight decay, dropout, and batch size for our two classifiers. We had a classifier for the 10x where it sees the architectural context, and a classifier for the 20x where it sees the cellular context. And then we want to optimize the parameters for each classifier. After Optuna provided us with the results, we then trained the model with the given parameters from Optuna, and we got a prediction for each patch for the image. Now we have, like, for one image you have 10 patches, 20 patches. We need to aggregate those patches to one prediction, so we use mean aggregation. We try different approaches like top k pooling, but mean aggregation gave the best results. After having the result at the patient level for the image, now we have two predictions, one for the 10x image and one for the 20x image. Here comes the late fusion model, where we basically had to get one grand prediction from the two classifiers. We used a weighted probability prediction, and to find the right weight or the right scale, we used the Breyer score for each classifier, and we took the lowest Breyer score for the 10x and 20x, and then we put them or plug in the given equation, and we get a final prediction for the probability of whether the 10x images and 20x images contain Mycosis fungoides or not. The results, as we display here, for the late fusion model, an accuracy of 77%. And an F2 score of 85%, and a very good sensitivity of 86%, which is very important for us on our research, because MF is a very deadly disease, and we were very careful not to miss any case. So we cared about sensitivity and the F2 score, 85% and 86% sensitivity. But as you can see here, the 10x model in the sensitivity outperformed the 20x model, which is why our paper is titled Context over Detail. It seems that the architectural context from the 10x images were much more important than the 20x cellular patterns. After that, the late fusion model as overall achieved an accuracy of 77%, and like the full comparisons and the metrics are displayed in our paper, but this is just a glimpse of the results, summarizing the most significant findings. Our end goal is to allow the dermatologist to be able to use our application, the one on the right, to diagnose immediately, as you will see in the following example.
I have your results here.
Okay.
And the diagnosis is benign.
So at the end, engineering is about improving lives. We have taken a complex, computationally heavy AI problem, and we packaged it into a one-tap solution where any doctor can use that. We are eliminating the diagnostic bottleneck, reducing the pathologist burnout, and ensuring that patients receive an early, accurate diagnosis that they need to survive. Thank you for your time.